Good morning, everybody. Welcome to a sunny but cold Wednesday morning of Chem 1105 with your host, me, Dr. White. Hi, everybody. Let me remind you, I have already sent out the email with the password for the password protected PDF file for test 3. You will have until 1 p.m. tomorrow, Thursday, I'm looking at the date, the 27th of April, to upload test number 3 as a single PDF file. If you don't, I reserve the right to take off a lot of points, and I will. And you can see right there that test 3 is all ready for you to go. There's the file, periodic table, and instructions in case you don't know how to upload a single PDF file, and the AppCam scammer in case you don't know how to use that or like to use that. While I'm here, let me remind you that the Chem 1105 extra credit project deadline is May 8th. Here's the extra credit project. I've already described it. If you need any help with that, email me or come to my office hour. It's 10, 10, 10 bonus points. So I want to move my video over here. So I would highly recommend do it. I'll talk more about it on Monday. All right, now let's get back to work. And don't forget, I do have my office hour tonight. If you have any questions about test number 3 while you're taking it, feel free to ask. Also, the review video, I have turned it off for now. After test number 3 deadline, I will turn it back on. Now, yesterday, I talked about acidic, basic, and neutral solutions. And this is something you should know. For acidic solution, the hydronium ion is greater than the hydroxide. And by the way, this is aqueous solutions only. For basic solution, that's a better bracket, the hydroxide is greater than the hydronium. And for neutral solution, the hydronium ion is equal to hydroxide ion. So if you have hydronium equal 1.0 times 10 to the minus fifth, and hydroxide equal 1.0 times 10 to the minus ninth, is this acidic, basic, or neutral? Well, you got to think there. This is not easy. Well, which is the larger number? Well, it turns out this one, so it would be acidic. But that was a lot of work. You have to know what's the difference between this and this. And that's a lot of work, and it's not easy. Well, good news. Someone came up with an idea, a concept that helps make it easier to find out, is the solution acidic, basic, or neutral? And that concept is called the pH concept. And probably of all the things I'll teach you this semester, this is probably one of the one or two or three most important things I will teach you. And because of that, and know this. All right, what is the pH scale? It's a scale of small numbers that's used to specify the molar hydronium ion concentration in an aqueous solution. I'll never ask on a test or final what's the pH scale, but I will ask you to know how to use it. By definition, the pH scale, pH equal minus the log of the hydronium ion concentration. So if you know the hydronium ion concentration, you can use your calculator, find the log of the hydronium ion concentration, then multiply it by -1. That's a lot of work. Well, don't tell anybody, but I'm going to give you a special gift. Shh, don't tell anybody. If the hydronium ion concentration is 1.0 times 10 to the minus x, then the pH will be x. If the number here in front of times 10 to the minus x is not 1.0, this is not true. On my test and final, it will be. So if you have a hydronium ion concentration 1.0 times 10 to the minus x, the pH will be x. Now, important things about pH. The pH range is from 0 to 14, never lower than 0, never higher than 14. Quick Dr. White story. Years ago, I was managing this one research. I had a number of PhDs and master's degrees and also bachelor degree chemists reporting to me. And hi, Maggie. But anyways, I had a master's degree chemist did this report where he measured some pHs of certain things that was part of his research. And at that company and all companies, before a report is issued, the manager has to proof it and actually literally sign off on a sheet of paper before it's distributed. So he gave me a copy of that and I read it and I called him into my office. And I was upset, really, which is unusual for me. Why was I upset? Because he had pHs in his report of 15, 16, and 17. It's never higher than 14. And I showed him that. I said, you know, you got a master's degree in chemistry. pH is never higher than 14. And there's an instrument we use in research labs and companies that measures the pH, but you got to calibrate it. He didn't calibrate it properly. And I said, if you ever give me a report, the pH is not 0 to 14, you're not going to be working here in 2 weeks. I promise that. Boy, I got his attention quick. And oh, I was fuming. And that's rare for me. So pH is never greater than 14, never less than 0. Now, the lower the number, the more acidic the solution is. The higher the number, the higher the pH, the more basic. This is a logarithmic scale. Each change of 1 pH is a power 10 times difference in the concentration of the hydronium ion. So pH change from 1 to 2 is a significant pH. All right, this is something you should know, pH scale. Let me move this out of the way. And the pH goes from 14 to 0. In the middle is 7. When you're at pH 7, that's neutral solution, neutral pH. That's when the hydronium ion concentration is equal to the hydroxide. When you're below 7, it's acidic. And that's when the hydronium is greater than the hydroxide. But seeing a number below 7, you know it's acidic, it's easier. If you're above 7, that's a basic solution. So pH 0 to 14. At 7, you're at neutral pH. Anything below 7 is acidic. The closer to 0 you are, the more acidic it is. Above 7, it's basic. The closer to 14 you are, the more basic it is. And let's look at a nice little chart on the internet. And you should all be able to see this. Let me check. Yep. And there are other charts you can find. But let's look at a few things. Water, if it's pure water, should have a pH of 7. You're not going to find that in your tap water. And below 7, the lower it is, the more acidic it is. Now, if you look at tomatoes, vinegar, and also lemon, those are acidic. Things that are acidic, certain substances like what's in a tomato, lemon, or vinegar has a very sour, tart taste to it. If you bite on a lemon, ooh, that's sour. Why? Because the pH is low, because there's an acid in there. And the acid is, I got a mental break now. Citric acid. Took me a second. And in vinegar, the acid is acetic acid. Citric acid is also in tomatoes. Now, in your stomach, you have cells that make hydrochloric acid. Hydrochloric acid is an acid, and because it's there, your stomach acid has a low pH because it's acidic. Now, if you go to the other end, if you look at bleach or drain cleaner or ammonia, ammonia is a base, the pH is basic. Now, another way of saying basic, they say on this chart, and I talked about it, is called alkaline. But I'll use basic for this class. And here's another one that gives you examples of things that are acidic, basic. What's another basic thing? I don't like this chart. I see some mistakes already. And here's another one again. And here they have alkaline. I'll use basic. This looks like the same one. Your blood is slightly basic, very close to neutral pH. And soda is also acidic. You should know this chart. Let me get subtle again. And what should you know? pH goes from 0 to 14. If the pH is 7, it's neutral. If it's below 7, it's acidic. And if it's above 7, it's basic. Let me rewrite this. Hang in there, I'm almost done. All right, is the following acidic, basic, or neutral? A liquid with a pH of 8. Well, what is that? Well, you should know the pH scale goes from 0 to 14. 7 is neutral. Below 7 is acidic. And above 7 is basic. So pH 8, it's above 7. This is a basic solution or alkaline. pH 2, it's below 7. This would be acidic. pH 7, whoa, pH 7, that's neutral. Now, let me remind you, pH equals minus the log of the hydronium ion concentration. And if H3O plus equals 1.0 times 10 to the minus x, pH equals x. This will be given to you on important information, test number 4. So, oh, okay, already did that. Let's start again. It's trying to combine too many things at one time, and it was going to work. This works better. All right, 5 points each. What is the pH of a solution if the hydronium ion concentration, H3O plus, is equal to 1.0 times 10 to the minus 4. And is it basic, acidic, or neutral? All right, what are you trying to find? pH. What are you given? The hydronium ion concentration equals this. And therefore, from important information, test number 4, you know pH equal minus the log. Later on, we have to identify is it acidic, basic, or neutral. Well, let's get the pH first. Is this. And we know the hydronium ion concentration this. And from important information, test number 4, I better open it up so you believe me. And you should see important information, test number 4. I give you the pH, then don't tell anybody I'm being nice. Shh. And if the hydronium ion concentration is 1.0 times 10 to the minus x, then the pH is x. So what's x? Well, it is 1.0 times 10 to the minus x, the hydronium ion concentration. Therefore, the pH is 4. That's the first thing. Is it acidic, neutral, or basic? And you should know this chart. I won't give it to you. This is one of the important things you should walk away from my class this semester knowing. It's like you know your own first name. I hope you know your own first name. And the pH was 4 for our problem. 4 is less than 7. Therefore, this is acidic. So let's look what we did. We found out, what are we trying to find? What are we given? We know pH minus the log of the hydronium ion concentration. We put it in. We know Dr. White's special gift to you. If the hydronium ion concentration is 10 to the minus x, then the pH 1.0 times 10 to the minus x, the pH is x. Well, in this case, 1.0 times 10 to the minus 4, x is 4, pH is 4, and it's less than 7, it's acidic. Let's do better. All right, let's do another one. I'll let you try doing this first. What is the pH of a solution if the hydronium ion concentration as H3O plus is 1.0 times 10 to the minus 12 and is acidic, basic, or neutral? We'll do it stepwise. First of all, your turn. What are we being asked to find? What are we given? All right, what are we trying to find? The pH. What are we given? The hydronium ion concentration is 1.0 times 10 to the minus 12. Now, we're trying to find pH in case you forgot. Remember, I've cut back on memorization. Test number 4, important information. pH equals minus the log of the hydronium ion. And if the hydronium ion is 1.0 times 10 to the minus x, the pH is x. So we now know pH equal minus the log, that's short for logarithm, of the hydronium ion concentration. And we know what that is. I'm going to let you figure out what's the pH. Let me just remind you this. If the hydronium ion concentration is 1.0 times 10 to the minus x, pH is x. Your turn. All right, well, the pH is 1.0 times, if the log hydronium ion concentration is 1.0 times 10 to the minus x, in this case, x is 12, and therefore the pH is x, which is 12. Now, is that acidic, basic, or neutral? Well, hopefully you'll learn this chart. When the pH is above 7, it's basic. And I hope you all agree 12 is greater than 7, so this would be basic. And that's how you do. Oh, let's do one more. Yep, 8 points. So the question is, if the pH of a solution, or if the, yeah, I'm getting ahead of myself. If the hydroxide ion concentration is 1.0 times 10 to the minus 10, what is the pH of the solution? And is it acidic, basic, or neutral? So what do? Well, what are we trying to find? pH. What are we given? Ooh, hydroxide ion concentration. But pH is equal to minus the log of the hydronium ion concentration. What am I to do? I don't have that. This is different from this. What do I do? Well, let's look at something you've already learned from me, and let's look at important information, test number 4. And here we have the ionization constant, Kw. Yay, no, it's not named after me, wish it was. That hydronium times hydroxide concentration equal 1. It really should be 1.0 times 10 to the minus 4. So what are we doing with this new information? We need to do 2 steps. Step number 1. We have to find the hydronium ion concentration, H3O plus. And how do we do that? Well, we know hydroxide times hydronium ion concentration. And it doesn't matter which order you put. You could have put the hydronium first, equal 1.0 times 10 to the minus 14. We want to solve for, look out, I'm going Technicolor on you, this. So we want it alone on one side. How do we get it alone on one side? Well, anything divided by itself equals the number 1, cancels out. So I want to get rid of the hydroxide to get the hydronium H3O plus alone on one side, so I'll divide by it. And that will cancel it out. Anything you divide one side, you have to do the other. And I will, and I did. This cancels out, because anything divided by itself is the number 1. 1 times hydronium is hydronium. We have this. I know this number from right here, so I'll put it in. What was it again? Minus 10. And this is 1.0 times 10 to the minus 4th. Am I done? No, I'm trying to find a pH. pH is minus the log of the hydronium ion concentration. So now I'm going to do step number 2. And I'm going to determine or calculate the pH. pH equal minus the log of the hydronium ion concentration. In step 1, we just calculated that. And when you have minus the log of 1.0 times 10 to the minus x, this is equal to x. What's x? 4. So the pH is 4. Is that acidic, neutral, or basic? You should know the pH scale. At 7 is neutral. Above 7 is basic. Below 7 is acidic. And therefore, 4 is less than 7. This is acidic. So when you're not given the hydronium ion concentration, but you are given the hydroxide, you need 2 steps. In the first one, you determine the hydronium ion concentration, and you use this right here to calculate it. Where do you get that number or that equation? From important information, test number 4. The hydronium ion concentration times hydroxide equals 1.0 times 10 to the minus 14. And that's how you do it. Oh, let's do another one. And I'll let you have some of the fun. Got ahead of myself. I've been doing that this morning. Sort of like when you play chess and you try and think a couple moves ahead, except you don't make the moves, you just think of the one ahead. One sec. All right, let's look at this. If the hydroxide ion concentration, OH minus 1.0 times 10 to the minus 2, what is the pH of the solution? And is it acidic, basic, or neutral? I'm going to do it stepwise. Actually, you are. What are you being asked to find? What are you given? Your turn. And what are you being asked to find? What are you given? All right. Well, what are we being asked to find? What is the pH of the solution? pH, what are you given? And from important information, test number 4, you know pH equals minus the log of the hydronium ion concentration. Wait a second, we didn't get that. So now you need 2 steps. And since we need the hydronium ion concentration, we've got to find it. And how do we find it in step 1? Hydronium ion concentration times hydroxide concentration equals 1.0 times 10 to the minus 14. That's the ionization constant of water. That's an important information. Test number 4. So we have to solve for hydronium ion concentration. To get it alone on one side, we have to get rid of the hydroxide. And I'll let you figure out, I almost did it. What's the next equation I was about to write for you? How do you get rid of hydroxide? OH minus. And the answer is you divide by OH minus to get rid of it, because anything divided by itself equals the number 1, cancels out. Whatever you do to one side, you have to do to the other. This cancels out. I have now my hydronium ion concentration, 1.0 times 10 to the minus 14th. equals the hydronium ion concentration. We know what that is. And if you take up your calculator, as I showed you yesterday, how you can do this in your head too, it's 1.0 times 10 to the minus 12. Are we done? No, we're trying to find the pH. We're given the hydronium ion concentration. And now you have to do step number 2. Determine or calculate the pH. And from important information, test number 4, pH equal minus the log of the hydronium ion concentration. We just figured that out right there. And when the hydronium ion concentration is 1.0 times 10 to the minus x, then the pH is x. So what's x here? 12. So that's my pH. Now, is it acidic, basic, or neutral? And here's the pH chart you should know. 7 is neutral pH. Below 7 is acidic. If the pH is, say, 3, that's acidic. Above 7 is basic. Hopefully, you all agree 12 is above 7, so this is a basic solution. Let's continue considering pH. All right, let's look at the following, 2 points each. What happens to the numerical value of the pH of a beaker of water at 7.0 if you add a few drops of concentrated H2SO4? Well, first of all, you have to know this is an acid. And in the pH scale, since I'm adding an acid, what happens to the pH? It decreases. So it goes down, and you can put an arrow down. And other synonyms for decrease. Ooh, fancy word from Dr. White. My English teacher from high school would be happy, or grade school. You could also say it gets lower. So when you add an acid to a liquid, the pH should go down. Now, what happens when you have a beaker of water and you add some concentrated KOH, potassium hydroxide? You should know this is a base. And when you add a base to water, the pH goes up. So what happens? The pH will increase. And you could show that by arrow up, or the word increase, or it gets larger. So when you add an acid, the solution gets more acidic, the pH goes down. When you add a base, the pH goes up. Now, there's something I shouldn't talk about right now that you know about what's acidic, what's basic, and what's all right. I'd like to talk about something that was a major problem in the United States back in the 1970s and 1980s, and also in Europe too. In about 1972, when we found out about it, and I'm talking about acid rain. What is acid rain? That's rain that's coming down and the pH is less than 7. And that shouldn't be. That's caused from pollution. And the pollution mainly was from power plants, burning coal and burning wood back in the 70s and 80s. And what they, as you see in the picture here, various pollutants, mainly sulfur dioxide and NOx, nitric oxides, and they would form in the air, in the clouds, react with the moisture to form sulfuric and nitric acid. And when it rained, I like my rain. But anyways, when it rains, it's not a laughing matter. The rain would come down and any of the crops or land or rivers would get acidic. If you're growing plants and you have acid rain, it's going to kill them or they're not going to do well. If you have fish in a lake or a river and the water gets acidic, you're going to kill off the fish. And luckily, due to our government back then had the, how should I say, courage to come up with rules for emissions. In other words, pollution control. It lowered the level of SO2 and other nitrous oxides going into the atmosphere greatly. And the acid rain problem was reduced greatly to almost, you don't hear about it that much anymore. So I wanted to talk about acid rain. That's when acid, like sulfuric or nitric acid, is formed in the clouds. And when it rains, it's in the water. And that's serious. And by knocking down the emissions from power plants, the pollution, we, the government and the country, were able to just solve the acid rain problem. That was mostly in the East Coast where they had a lot of power plants. And also, even the Midwest power plants, the pollution would go east and pollute the land there with acid water, acidic water. With that, I'm going to take a 5-minute break. I'll see you in 5 minutes and we'll continue. let's get back to work. All right. Now, we were talking about acids and bases. And that's not the slide I want. And we did our pH practice time. Let's talk about what's called acid-base titrations. And an acid-base titration is a neutralization reaction in which a measured volume of acid or base of known concentration is completely reacted with a measured volume of an acid or base with an unknown concentration. And by doing a titration, you can determine what is the unknown concentration of that acid or base. Now, let's talk about a acid-base reaction. We have an acid and a base. They'll react to form this salt. Now, if you start out with an acid and you add enough base so all the acid reacts with the base, and if there's strong acid and base, what really happens is this. Most of it goes to the right. Now, think about this. You have some acid. It's reacting with your base. This is an equilibrium arrow, not a minus sign. Let me move it. I'm going to have to do something. This happens once in a while. I've got so many files open. I've got to close some so some of them get closed. We're up to speed on here. Let me open up the other. Sorry about that. It happens once in a while. All right, let's get back to this. If we have an acid plus a base and they're strong, the equilibrium, or mainly you go to the right. And when you're consuming, reacting the acid, there's less acid. That means this is disappearing. And what happens is when all of the HA reacts with B to form A minus and HB plus, the pH equals 7, neutral. And at that point, you need the same number of moles of acid as base when it's neutral pH, and that's why this is called neutralization, because you're moving the pH to neutral pH, or the acid concentrate type of solution. So How do we do this? Well, it turns out, and you'll be doing this in a lab next week, you have what's called a pH indicator. And a pH indicator changes color depending on the pH it is. Now, there's one famous pH indicator that changes pH at 7.0, and that's called phenolphthalein. And phenolphthalein below 7 is colorless or clear. At just above 7, like 7.001, I mean, just one molecule above it, above 7.0, the phenolphthalein, if it's in a solution with the acid and base you're reacting, is now a rose color or a red wine color. I've never done this before, so it's a first. They call it pink. Here we go. It turns this color fuchsia or pink. Below that is clear. So when you're adding a base and acid or acid and base, and you have phenolphthalein in the solution, if it's clear, it's still acidic. As soon as you see the faintest color, you've known you've just gone right above pH 7. And this helps us do what's called titrations. And titration data are used to calculate the molarity of an acid or a base of the solution. Now, key points, titration points. At neutral pH, just when the indicator changes color, you can calculate the moles of the known molarity acid or base. Based on the neutralization reaction, you can determine how many moles of an unknown molarity acid or base was present in the volume of the sample of the unknown acid or base. In other words, if you have a known acid and an unknown base, you can titrate to get the molarity of the base. If you have an unknown acid but a known base, you can titrate it, and when using the indicator, find the molarity of your acid. Now, if you know the volume of the unknown acid or base and the moles in that sample, you can calculate the molarity of that acid or base that's unknown. Now, don't tell anybody, but I'm going to show you how to do for certain types of acid and bases the simple way to determine the unknown molarity of the acid or base with a titration. Shh, don't tell anybody, and be nice. Remember, now, turns out certain acids can give up more than one proton. It's called monoprotic or diprotic. I'm going to just do monoprotic. This only works for monoprotic, and that's all I'll ever give you on a test. Let's look at the following. All right, let's take a look at this. If it takes 251 milliliters, and by the way, 10 points, if it takes, and this we're talking about test number 4 material of questions, if it takes 251 milliliters of a 1.76 capital M molar NaOH solution to neutralize 378 milliliters of an HCl solution, then what is the molarity of the HCl solution? So what are we trying to find? The molarity of the HCl solution. As soon as you're trying to find a molarity, you know this is a titration problem. What are you given? You have 378 milliliters of a 1.76, remember capital M means molarity, NaOH solution. And you also have 307, I got this number wrong. And this is where it pays to show your work. If you had done that, this should be 251. You have 251 milliliters of a 1.76 NaOH solution. And you also have, you're neutralizing 376 milliliters of the HCl solution. So what do? Well, at neutralization, you know moles of acid equals moles of base. And I've simplified this to help you with the next step. What are moles of acid? Milliliters of acid times the molarity of acid. I could derive and show you how I came up with this, but for this class, just trust Dr. White. Do you? I hope you do. And that's equal to milliliters base times molarity of base. And as I said, I've asked you to cut down on memorization. Oops, got to open one more thing. If you look at test number 4, important information, titrations at neutralization, moles of acid equals moles of base. Again, this is for monoprotic acids, which we'll only use in this class. And I show you milliliters of acid times molarity of acid equals milliliters of base times molarity of base. Now, what's the acid? You should know hydrochloric acid. So we know we have 376 milliliters of acid, HCl, and we're trying to find the molarity of the acid. This we have to determine. What's the milliliters of the base? Well, the base is NaOH. That's 251 milliliters NaOH times the molarity, 1.76 molar NaOH. And we want to solve for this. How do we get it alone on one side? Anything divided by itself equals the number 1. Therefore, to get rid of this, because I want this alone on one side, I'll divide by that. But whatever I do to one side, I have to do to the other. This cancels out. I'm left with the molarity of HCl, which is what I'm trying to find, equals 251 milliliters. I won't write NaOH, 1.76 molar NaOH divided by 376 milliliters. Milliliters cancel out. I'm left with molarity, ignore the NaOH. And now I can pick up my calculator and find out what that number is. And the number my calculator gives me is this. And remember, on all my tests, and it'll be true for test number 4, it will say, please use proper significant figures for all calculated answers. This is 3 significant figures. Remember, all non-zero numbers are significant. 3 significant figures and 3 significant figures. Oh, I'm in that rut again. And you round the answer off to 3 significant figures. I'll give you 3 seconds. I'll give you 6 seconds to do it. Bonus time. Time's up. By the way, this is a 4. So keep the 1, keep the 1, keep the 7. Is that 4 or less? Well, it's 4. Therefore, you drop all this. So it's 1.17 times 10 to the 0, which you know 10 to the 0 is 1. You can leave it like this, or you can also write it like this. And that's the molarity of the unknown HCl solution. And that's how you do titrations. Let's go through this again. You find out, what are you being asked to find? Molarity of HCl. As soon as you see you're trying to find a molarity of HCl, and you're given also a base, NaOH, or vice versa, it's a titration problem. And the key to that is when you see the word neutralization or the pH indicator changes color. So at neutralization, moles of acid equal moles of base. And the moles of acid is milliliters times acid times molarity. The moles of base is milliliters of base times molarity of base. We put in those numbers. This is the unknown we're trying to find. We get it alone on one side by dividing the number we're trying to get rid of, and you do the calculation. And that's how you do a titration. Let's do one more. All right, let's take a look at this one. Now I'm going to try something different now, but let me read the problem. If it takes 751 milliliters of 1.76 times 10 to the 2 capital M, that's molarity HCl solution, to neutralize 351 milliliters of a KOH solution, then what is the molarity of the KOH solution? And what I'm going to try different now is, if you're watching the video, before you hit pause, determine what are you trying to find and what are you given. Hit pause. By the way, you can turn it on now. Let's assume you had time to figure it out. We're trying to find the molarity of the KOH. Molarity, KOH. What are we given? Well, we have 751 milliliters of a 1.76 times 10 squared molar, that's the capital M, HCl solution. And that neutralizes 351 milliliters of the KOH solution. As soon as you see the term neutralization and you're trying to find molarity, this is a titration. And it's 10 points too. And what do? You go to important information, test number 4, at neutralization, moles of acid equal moles of base. That's milliliters of acid times molarity of acid equals milliliters of base times molarity of base. Years ago, when I taught, a couple of years ago, 1105, you would have to memorize that. Now I'm giving it to you in important information. Test number 4. So, at neutralization, moles of acid equal moles of base, which is equal to milliliters of acid times molarity of acid. Oops, I'm getting ahead of myself again. Equals milliliters of base times molarity of base. KOH, you should know, is a base. HCl, hydrochloric acid, that's in your stomach, that makes your pH of your stomach low, but we're doing a titration as that. So now I'm going to milliliters of acid, 751 milliliters. Molarity of base, equal milliliters of, or molarity of acid should have been here, and I did, and times the equal the milliliters of base. Remember, KOH is your base, and we're trying to find the molarity of the KOH. Now, I'm going to rewrite this real quick. You don't have to, but to help you understand what I'm doing, all I'm doing is flipping it. So we're trying to solve for molarity of KOH. I forgot the M there. And we want to get rid of the 351. So I'll divide by 351, because anything divided by itself is the number 1. It's canceled out. But whatever I do to one side, I have to do to the other. This cancels out. So I have the molarity, KOH, equals 751 milliliters times the molarity of the HCl, divided by the milliliters of the base, KOH. Milliliters cancel out, I'm left with a molarity. And now I can pick up my calculator, clear it. Don't forget, use blue double E for 10 to the minus 2, or 10 to the 2. And I get this number. And this is 3 significant figures, 3 significant figures, I'm in my rut again. Round this off to 3 significant figures. Yep. Keep the 3, keep the 7, keep the 6. Use the 5 to round off. Is that 4 or less or 5 or higher? And 5 or higher. Drop all this, increase this by 1. And the answer is 3.776 times 10 squared molar KOH solution. And that's how you do titration. Now, it turns out titrations like this are used to measure things in industry with other tests. And at one company I was hired, actually 2 of them, they did a lot of titrations, but they were having problems. And I helped them straighten out the problems by bringing in electronic, what's called burettes, that measure volume accurately to 1,000.001 milliliters, so they could do accurate titrations. And it saved a lot of money. At the other company, I helped them automate titrations, because every morning the chemists would do about 100 titrations to analyze the quality of different products and tanks. And that saved a lot of money. All right, now in this chapter, there's one last thing I want to talk about, and that's buffers. There's something called a buffer solution. I'll be subtle again. You should know this, know this. Now, a buffer solution is a solution that resists major changes in pH when a small amount of acid or base are added to it. This is what you should know. Now, I won't go into it in this class, but buffers are the acid and conjugate bases of weak acids. Yeah, but the key thing you should know is when you add a small amount of an acid or base to buffer solution, the pH does not change. I'll say it again. When you add a small amount of an acid or base to a buffer solution, the pH does not change. Hang in there. I got a few more words to go. All right, let's look at this. 2 points each. What happens to the numerical value of, I forgot something, of the pH? It should go right there. What happens to the numerical value of the pH of a buffer solution if you add a few drops of a dilute solution of, and the first one is H2SO4. And you should know that's an acid, but it's a buffer solution. And we're adding a small amount, dilute solution of H2SO4, buffer solution. By definition, you add a small amount of acid or base, it stays the same. Therefore, the pH, the numerical value stays the same, or you could put down does not change. Now, let's look at B. What happens to the numerical value of the pH of a buffer solution if you add a few drops of a dilute solution of NaOH? Well, this is a base. However, we have a buffer solution. When you add a small amount of an acid or base to buffer solution, what happens to the pH? It stays the same. By the way, your blood is a buffered solution. If your pH of your blood gets too high, you have what's known as acidosis, and it'll probably kill you. If it gets too low, I don't know what the base name is. If the pH is too low, it's acidic. Acidosis, too high, I don't know what they call that. Let's find out. Alkalosis, that's what it's called. And if that happens, gets too high or too low, you're dead. Now, there's a famous movie in the first version I like better than the newer recent version called The Andromeda Strain, and that deals with how the pH of the blood did something amazing. And I'm not going to give away the movie. You'll have to watch it. It's The Andromeda Strain. Watch the older one from the 1970s. Awesome movie. All right. With that, the end. We finish chapter on 7 acids and bases. Now, next Tuesday, I will go through chapter 7 problem set. If you look at the syllabus, I have the test number 4 on Wednesday. I'm going to move it to a new date, probably the following Monday, because I still have to go through organic chemistry in a couple of days. And I'm going to start that right now. Let me first open up that chapter. All right. Now, this is from chapters 9, 10, 16, 17, 18 of your book. And I teach at this school. I have taught, like last summer, I taught it. Chem 1212, and for many years I've taught it here. And at another school, I teach a one-semester organic survey course. And that's pretty quick. I'm going to just give you a taste of organic chemistry. And if I look like I'm having a lot of fun, I am, because I am an organic chemist. Now, what is organic chemistry? And the switch is off for this. It's initially study of molecules that were found in things that were alive, like plants, animals, and us, humans. And turned out in 1808, a German chemist made the first organic molecule from inorganic molecules, which was a great breakthrough. Inorganic means molecules that are from things that were never alive, like sodium chloride. Now, today, organic chemistry is really defined as the study of molecules containing carbon and other atoms, mainly hydrogen. Now, the most important thing about carbon, which you learn, it has 4 valence electrons. And it can bond to other elements, and this is very rare, including itself. Now, that alone isn't that rare, but the next point is carbon atoms can form chains like I wear around my neck, or my jewelry chain, or bicycle chains. They call it a chain because it's linked together. And these can be straight chains with branches, like you see branches of a tree, or in what we call rings. And it's the basis for all life on Earth. We're carbon-based life. Now, there's some definitions I want you to know. And this in the next slide, you should know. When we start out in organic chemistry, we talk about hydrocarbons. Those are molecules with only carbon and hydrogen atoms. If you've been following what would be the right term, all the news about pollution over the last decade or longer, one of the key sources of pollution are hydrocarbons. And those are molecules that only have carbon and hydrogen atoms. Now, I don't know if I'll get to it today, but here's an example. Now, up to now, we've used empirical formulas, but now I'm going to show detailed formulas. And this way of writing, you could also write it this way. And each line is a pair of electrons, a covalent bond. And this is propane. That's the name of this chemical. Oh, you know propane. It's used for your barbecue. That's the stuff in the white tanks that you burn to cook your food in your barbecue. You have a propane barbecue. And propane has 3 carbons and 8 hydrogens. Notice each carbon has 4 bonds to it, because carbon always has 4 bonds to it. 1, 2, 3, 4. This carbon, 3 hydrogens, and a bond to another carbon, and they're linked together in chains. You should know a hydrocarbon is a molecule with only carbon and hydrogen atoms. Now, there are 2 types of hydrocarbons you should know. And this part, I'm going to ask you to memorize a few things, but this is in our daily life. Now, the two types are saturated hydrocarbons. Those are molecules because it's a hydrocarbon with only carbon and hydrogen atoms. But because it's a saturated hydrocarbon, it's a molecule with only carbon and hydrogen atoms, in which all carbon, this is important, carbon-carbon bonds are single bonds. And you know that's one pair of electrons being shown. And we show a single bond in organic chemistry by a line between two carbons. That line is a pair of electrons. Now, the other one is unsaturated hydrocarbon. Because it's a hydrocarbon, it's a molecule with only carbon and hydrogen atoms, and it contains one or more, now something new, carbon-carbon multiple bond, which can be a double bond, two pair electrons, or a triple bond. We show a double bond by two lines between two carbons. Each line is a pair of electrons, and a triple bond, three pair of electrons. So a molecule with only carbon hydrogen atoms that contains either a double bond or triple bond between two carbon atoms is an unsaturated hydrocarbon. And I'll talk later about unsaturated fats, and that deals with double bonds between carbons. So saturated hydrocarbon, molecule with only carbon hydrogen atoms, in which carbon-carbon bonds are all single bonds. Unsaturated hydrocarbon is a molecule with only carbon hydrogen atoms that contain one or more carbon-carbon multiple bonds that can be a double or triple bond. You should know this. Now, how do we draw organic molecules? And this is going to be something you should be familiar with. Now, there's the condensed structure, and I won't ask you names, what's condensed structure, and condensed structure with parentheses. Now, the condensed structure is how atoms are connected. And the condensed structure with parentheses are because organic chemists are lazy. We are. And it helps shorten when you have a lot of carbons and you have repeating units. See board, for example. Now, let's assume we have a hydrocarbon or molecule with 4 carbons, and they're bonded together. Now, there's always 4 bonds to carbon. We look at this carbon, this is going to be a high math time, and you better get your calculator out. You have here 1 bond to carbon, that's that line. So if there are 4 bonds to carbon, 4 minus 1 equals 3. And when there are not 4 bonds to carbon, we add hydrogens to bring it up to 4 for a hydrocarbon or any molecule with carbons in it. And that's how you do this. We look at the next carbon. There are 2 bonds to carbon, but there should always be 4. 4 minus 2 equal 2. So this carbon will also have 2 hydrogen. Same thing for this one. 4 minus 2. This carbon here has 1 bond. There should always be 4. Therefore, there's going to be 3 hydrogens. Now, this molecule, which is called butane, and you don't have to know the name, but that's the liquid in those little lighters. This is called the expanded view. If we look at this carbon here, there are 3 hydrogens. The condensed view is you write the 3 hydrogens like that. The next carbon has 2 hydrogens, and you write it like this. And the third one has 2 hydrogens, and you write it like that. And this last carbon here has 1, 2, 3 hydrogens, and you write it like these are the same. This is a condensed form, and that's easier to draw. Remember, there are 4 bonds to carbon always, and if they're not, you add hydrogens like I did there. Now, with parentheses, let's look at this molecule. And notice there's 1, 2, 3, 4, 5, 6, 7, 8 carbons in it. This is a hydrocarbon because there's only carbon and hydrogen atoms. This is a saturated hydrocarbon because between the two C's carbon atoms, there's only one line, single bonds. And this is called octane. Octane, I've heard that name before. Oh, when you go to the gas station, you see the octane number. And this, and I'll teach you later, isomers of octane are a main component in gasoline. But what I like to show you is parentheses, which I won't ask you to do, but you may see. Notice there's 1 CH2, 2, 3, 4, 5, 6. And because organic chemists are lazy, that was a long time to write. Sometimes you'll use parentheses, CH2 connect together is repeated how many times? 1, 2, 3, 4, 5, 6. And we'll do that. And this is another way of doing that. Now, if you had 12 or 14 of those CH2s, and there are molecules that, this is an easier way of doing that. You change the 6 to 12 or 14. Both of those are ways. This is the condensed form with parentheses. This is the condensed. For my class, most of the time, and when I teach organic, I write it this way. There are other ways too. But if I look at the clock, we're out of time. And let me remind you, I've already sent out the password for test number 3. You'll have until tomorrow, 1 p.m. to take test number 3 and upload as a single PDF file. Don't forget, this weekend, I'd highly recommend you work on the extra credit project. As I mentioned before, email me your project before you upload it to Blackboard. I'll check it and see if it's right. If there's something wrong, I'll tell you so you can change it so you can get 10. Notice my eyes are going real wide. Yep, 10 bonus points. That's like getting 10 more points on a test. And with that, don't forget, hand in your labs. Tomorrow is the deadline for the lab amnesty program. So hand it in by the end of tomorrow evening. And if you have any questions, come to my office hours. With that, if there's any students who'd like to stay a little late and ask any questions, I'll stick around. If not, I'll say, Gang gesund. Bye now. I stole that from Granny to Beverly Hillbillies. Gang gesund. Goodbye. Remember, gang gesund means go in hell. And the pandemic, even though they say it's over, I'm still wearing my mask.